Well, I want to clear up our two definitions for work with this example. Let's say you're pulling an object up a steady incline by pulling on a rope. Then the vector that represents the force would be this red vector here, pointing in the direction that the rope is pulling. And the displacement, of course, is going to be parallel to the incline. So we can define some angle theta that represents the angle between the displacement vector and the force vector. So notice we've put the two vectors of force and displacement so that their tails coincide. So the best approach here would be to let the axis of the displacement be the x-axis. If that's the case, then the displacement has no component along the y-axis, although the force does, right? So we could break this force vector into two components. It has a component this way, which would be F parallel to the displacement, and there's a component this way, which would be F perpendicular to the displacement. And the end result is that this component of the force does no work, and this component does some work. And the way we would calculate this component, it would simply be F times cosine theta. And of course that means this component would be F times sine theta. So in the end, the amount of work done is actually F cosine theta multiplied by the displacement. So let's go over here and take a look at our two definitions for work. So one of our definitions is work is a vector dot product of force and displacement. If the force is constant, then we write that as an equation. Work, which is a scalar quantity, is equal to the vector force dot product with the vector displacement. Here I have D, and we could just as well change that to a delta S. Same thing here. Yeah, so the end result of taking the vector dot product is it's the component of force parallel to the displacement, F cosine theta, multiplied by the displacement. Now, if the force varies over the displacement, if you pull light at first, then pull harder, and for every meter along the displacement, there's a different amount of force, we can still calculate it by taking an integral of the force dot product with all the little incremental bits of displacement. And then in the same way, we can get rid of the vector nature of this equation by just multiplying the magnitude of the force times the magnitude of the incremental displacements multiplied by cosine theta. So that's the mathematical way that we define work. In concept, it turns out that work is always equal to some sort of change in energy. So for example, I showed you this device called the thigh master before. So if I do work, if I just exert a force and hold it there, I'm not doing any work. But while I compressed it, my force matched up with some sort of displacement. Now where's the energy? I don't know, I could take this baseball out of my back pocket, and I suppose if I pulled this back and set the ball in here, I'm not gonna do it because I might break something, but you know what would happen. As soon as I release it, that potential energy stored in the spring of this device could put this ball in motion. And likewise, if I were to just hold the ball like this, I'm exerting a force in this direction, but I'm not doing any work. But if I take the baseball and I throw it, well then I'm exerting a force and I'm displacing the ball, and certainly that would result in an increase in the ball's kinetic energy. What are some other examples of change in energy? Oh, if I just take my hands and rub them together, I'm overcoming a force of friction. And there's definitely a displacement involved here, and I can feel the thermal energy that's being produced in that case. If I take a child's toy like this balsa glider, as I twist the propeller, I'm applying a small force, but the force is there, and that force is overcoming the elasticity in this rubber band, and the more work I do, the farther I displace it with that force, the more the rubber band gets twisted up, And certainly there's some sort of energy stored here, because if I let it go, it has the ability to spin the propeller back and I can make this thing fly through the air. My work could even produce some form of electrical energy. So if I turn some of these light bulbs on, crank the handle, I'm applying a force through a displacement, and you can see the electrical energy that results. So that's it. We will probably rely on this definition of work more often than not, because the emphasis of this course is to make calculations. But keep in mind, whatever the work calculates out to can always be set equal to some sort of change in energy. Thanks for watching.